today we're going to talk about advanced process control. I'm going to really make it simple for us, or as simple as I can. So what is it and why is it important? And how does it apply to different industries? So really try to make it basic. Most of the videos when I look up advanced process control, they go straight into all the mathematics. So I'm going to try to make it nice and simple for us. So what is advanced process control? We're going to go into analogies. So think of it as like the smarts on top of something. So like an easy way to think of it is people are familiar with going from an Uber to Waymo, like a fully autonomous car. So the additional smarts that enable the fully autonomous bit, that is considered your advanced process control part of it. Now, of course, that's in cars, completely different. I'm aware for all the people who are going to go into, all the people who are into, want to be purist on it. But that's essentially an easier way to understand what it is. It is really common in other industries, and we'll go through that. But really, advanced process control is that additional control layer that's supervising and executing based on what it knows at that level. So to start off, though, there are also basic control systems. So PID, programmable integral derivative control. So this is the typical control that you will see at your PLC level, so your programmable logic control level. So in midstream, that would be at a pump station or a compressor station. So you have your programmable logic control that will be operating and executing your PIDs. So those PID loops are the closed loop control. So a really simple example of like a closed loop control would be if you have a sensor, your backup sensor on your car. As soon as it starts censoring that it's coming closer, then the frequency of the beeps will increase. So that's an example of closed loop control. In a pipeline scenario, what that means is the control room operator will set a suction or discharge pressure set point, and then the PID will ensure that the pump variable frequency drive either speeds up or slows down to achieve that goal, or the valve opens or closes to achieve that goal that the control room operator set. So in this type of scenario, then an advanced system would be, okay, you have the original programmable, PID loops, and you're executing at the pump stations. Well, in midstream pipelines, there are multiple pump stations. They kind of continue on. They can continue on for a really long time. So being able to then, the way that the control room operator operates is they're thinking about that from a mental model, and they're executing to achieve a certain flow rate on that pipeline. Now, what an advanced control system does is it will calculate what the theoretical hydraulic max is, and then execute an algorithm or a series of algorithms to bring set the set points to bring the flow rate slowly up to what that is. So same as a mental model and like a human would be doing. So think of it, an easy way to think of this one is think about pilots, and you're flying a plane. So imagine you're actually flying the plane, and you have, you're actually flying it versus there being an autopilot software. So that's your difference in terms of the level of control of an advanced package versus like a basic control system. So some people do get confused as well. They're like, okay, well, I have SCADA. That's my advanced control system in the midstream. And no, it's not, because SCADA can only issue and receive commands. It can't actually execute on much control beyond a script or some if statements. So it doesn't have the types of algorithms that would be found at, say, like a DCS or a distributed control system. Why is it that industry needs advanced control? Well, people are running these mental models, and they're constantly tweaking and pushing these buttons. Well, we need advanced control because humans make mistakes. I believe it's like 80% of the incidents, safety and environmental in the industry are caused by human error. So we're well aware of that. We know the safety implications and the safety benefits we get from automated systems. So it's definitely something that we're all aware of as a society, and we're moving towards. So why we need advanced control in heavy industry is because heavy industry is, it's called heavy industry. Like, it's big and scary and dangerous. So it's even more important that we have the correct levels of automation from a safety perspective. So what are some key techniques in advanced process control? Model predictive control is one of them. That is a set of algorithms that take a process model and then predict out what steps would need to be taken to move to the next state in that model. So this is the predictive control. Exactly what Crux does. This is what enables industrial autonomy. Multivariable control then can handle many in and many inputs and many outputs, as opposed to your traditional PID, which handles just one input, one output. Process models are the foundational mathematical physics-based models that feed these types of systems, or that we will test for these types of systems. Another word for this is the digital twin. Folks like to think of it as the digital twin. Optimization algorithms, so seeking a global optimum for something, say a minimization of energy usage or maximization of throughput. Those are algorithms that are also a part of the advanced process control umbrella. Real-time data integration, absolutely part of the advanced process control umbrella. So we have to have some sort of data feed in locally at the edge to ensure that the algorithms keep executing the way that they are designed to. Applications of advanced process control in different industries. Industries you may not even think of. So the semiconductor manufacturing industry actually heavily leverages advanced process control. Chemical processing heavily leverages advanced process control. So think of where do you get your shampoo or your plastics from. Those industries heavily leverage advanced process control. Oil and gas, of course, the energy industry heavily leverages advanced process control, specifically in refining and fracking facilities, very heavily used. Power generation, so think your hydro facilities or like a cogen, natural gas-fired cogen plants, complex control systems required on turbines, so lots of leveraging of advanced control. Renewable energy, depending on the way that solar fields are set up, renewable energy like hydro, all of that will be leveraging advanced control. Utilities, of course, utilities have pipelines as well. So, hopefully they'd be working with Crux and also have advanced control. And then, of course, data center energy management actually is also an advanced control application that folks may not be as aware of. So what are the benefits of advanced control? I hope they're a little bit obvious because I think when we go to my favorite analogy again with pilots, we love autopilot software. Like we're not getting in a commercial flight without it. So we love it. But increased profitability and throughput. So typical APC packages see about 50% utilization and additional throughput between 3 to 5%. So those are fantastic, well-proven over 30 years returns that folks are seeing. Lower costs, of course. So lowering costs. Using advanced control minimizes your energy usage, which is going to minimize your costs. Improve product quality. Decreasing that variability in production is hugely valuable to decreasing any sorts of anomalies in products that folks are selling. And it's super important that products are the highest quality for our customers. Maximized operational efficiency, so making sure that we're getting the most out of our assets. We want to be running as close to 100% utilization of our assets as we can, with, of course, room for maintenance and upsets. Enhanced safety and reliability, so having the computer and having an automation platform in place drastically reduces the probability of an upset or an incident due to human error. So really valuable to have that level of automation. Hands-off operation. So to elaborate a little more on that, having folks not having to actively press buttons. Humans make mistakes. Ensuring that mistakes aren't made, hugely valuable to the business. So possible challenges with implementing APC. Definitely significant around the management of change. Integration as well with legacy systems is probably the biggest challenge. Legacy systems aren't built to have data feeds in and out of them. Not that we want data feeds into the OT environment, but definitely out. So they're built that way. And so that creates a challenge for implementing something like advanced process control. Sometimes the economic justification may not be there for an asset, say a pipeline asset that's not apportioned. Maybe it's not valuable to get more throughput on that line. Therefore, putting on an application like MaxOpt for that use case is not actually valuable. So the economic justification may not be there depending on the specific operation. Shortage of skilled workers is definitely a challenge. Anecdotally, there was a control room manager that I know quite well. He told me back 5 years ago he'd get 300 job applications for a control room operator position. He told me a couple years ago that he'd only gotten 8 for a job that he had posted. So that reduction in skilled workforce is really starting to happen, and I think operators are starting to feel that. So it's even more important to put in in packages like APC to start being able to automate and capture that value and capture that knowledge in the business. Data quality and availability is also a challenge to successfully implementing advanced control systems. For example, I know of some gas pipeline systems that are not, their actuators are not telemetered back to the SCADA system. So a control room operator has to actually do a phone call out to the site to have someone go and operate that asset. So data quality and availability it's not possible to get that data and have that feedback loop tight enough to enable an advanced system. It just doesn't make sense in that type of a case. APC implementations can also fail due to tight timelines. Everybody wants everything fast, then they want more. So like any project, any large capital project, APC implementations can also simply fail due to too tight timelines and not being able to meet them. Budgetary constraints as well. So initial costs of standing up an APC system may be so significant that it doesn't make sense in the annual budget, despite the benefits that will be seen in years 2, 3, and ongoing. Resistance to change. So a lot of what we hear too is, well, we've always done it this way. That we understand if it's not broken, don't fix it. But if we don't get better, we go the way of the dinosaur, and we don't really want that either. So we need to find the balance in between. Maintenance and performance degradation as well. So APC systems, especially when they're only installed on-prem, if you have some more connectivity, things can be different. But if they're only installed on-prem, over time they become less effective due to equipment changes or changes in operation, which is really unfortunate, but can be a reason why these systems might be taken out over time. Okay, best practices for APC implementation. So the first one is setting clear KPIs and acceptance criteria. So super important. That's super important. That's why it's number one. So setting what is it that means success, right? What percentage of throughput and how are you measuring that? And has everyone agreed to it and documented it? That's super important for the success of these types of programs. Conducting a thorough process analysis. So making sure that the design phase up front of how it's going to be configured, how the control system is going to be allocated, exactly how that's going to roll out, making sure that all the historical data has been collected, the control narrative is understood, and that the process is started to be able to set up the APC. So selecting the appropriate control strategies, that's different depending on the asset. So if it's a pharmaceuticals facility versus a pipeline versus a chemical plant, you would be using different components of the advanced control, different algorithms, different methodologies of advanced control to be successful in executing, to make sure you choose the right one. Engaging cross-functional collaboration. So a lot of the times, the control room operator gets forgotten in these processes. Definitely not what we want. But we also cannot forget cross collaboration. So maybe it's the SCADA or the DCS team. Maybe it's the production engineering team. Maybe it's IT. Making sure that all of these different stakeholders are properly engaged throughout the process. Plan a phased implementation. So what does success look like for phase 1 and how is it measured? Okay, roll that out. What does success look like for phase 2 and how's it measured? Okay, roll that out. So phased implementation definitely help increase the probability of success. Ensuring seamless integration. This is primarily from the end user's perspective. You don't want it to be clunky for them to have to turn on this type of system and don't want to have to change much in front of their screen. So things need to be consistent and simplified for them. So that seamless integration from the end user's perspective is super important. Okay, so providing comprehensive training for the end user specifically, but if it comes to installing an advanced control package, comprehensive training is super important to guarantee success. Monitor and maintain performance. So we need to make sure that we're monitoring these types of packages, making sure that we understand how the end users are using them, what the utilization is, if it can be improved upon, because that's value for clients. So making sure that that is set up and that it can be monitored will help ensure success of these types of programs. And then plan for scalability and flexibility. So how are we going to roll out across multiple assets, multiple refineries, multiple chemical plants, or within a specific chemical plant, roll out to more of the different units. So that's something that needs to be planned and thought of in advance to make sure that your advanced control rollout is successful. Criteria for selecting efficient APC software. What does that look like? industry-specific applicability is really important. A lot of packages have been built horizontally and in theory can apply to different verticals. In reality, that's not quite the case. So a package that is built for pharma is much more specific and better suited towards pharma versus an oil pipeline application and something like that. The two applications, yes, they may have the same algorithms in them, but that doesn't mean that they work the same or that they're as easy to install. So you really want to look at an industry-specific vertical package. You want to look for advanced features. So is it just a base model predictive control, or can you do these different things? Does it have modern microservices capabilities and API connectivity? So that's the stuff that we need to be thinking about for when selecting the correct software. Vendor reputation and support. So is there a support program in place? Something to be aware of is a perpetual license. We'll have a very minimal support package with it, whereas something that has an annual recurring fee will have more robust support for sure. Ease of use, especially from the end user, is it easy for them to use? Is it easy for them to engage? When it comes to installing it, yes, we want it to be easy, but really it's about that end user at the end of the day. Cost versus ROI. So when selecting the package, we want to make sure that the cost of that package is going to provide the desired return on investment, dollars and cents at the end of the day. And then real-time monitoring capabilities. So, there's lots of packages that have optimization capabilities, but can it do real-time monitoring and control? If it can't, then it's not actually an advanced control package. What about proprietary, so in-house built advanced control solutions versus third-party? Well, in-house solutions, while they're great, it's an in-house, you could think of it as an in-house application. I know people think of advanced controls differently, but it's still code written as software with mathematics. So think of it from an in-house solution versus any sort of third-party solution. It comes down to build versus buy. What should you do? Well, if you can build and maintain in-house for a lower cost than to buy, then of course it makes sense to build in-house. However, in these types of algorithms exist, they are standardized, and third-party teams bring significantly more expertise to keeping these types of software up to snuff and at the top of their game. So I think in the advanced control world, you definitely would want to buy versus build. Obviously, I'm biased, but if you're going to build, you're building a software company, and most chemical processing facilities or pharma or semiconductors, they're not control systems companies. So they are different disciplines. In conclusion, that is everything that I know, I hope, about advanced process control. Hopefully just explained in a way that is friendly for the midstream folks that listen to us and in oil and gas. Yes, so please like and subscribe. Let us know what experiences you folks have, getting to know this type of technology, and hopefully you already know it, and that's great. And then please correct me if I said anything wrong. So please find us on LinkedIn, find us on YouTube, like and subscribe. My name is Vicky, and we are Crux. Thank you.